What if the universe itself prevents us from ever knowing everything? This isn't just a philosophical question, it's a fundamental truth about the nature of reality itself. At the smallest scales of existence, where particles dance in probabilities and waves collapse into matter, we encounter a profound and unsettling limitation. The universe refuses to be pinned down. It holds its secrets close, whispering possibilities rather than certainties, leaving us to wonder whether complete knowledge is even possible. This idea might feel unsettling at first, but it's also what makes our quest for understanding so deeply human, so relentlessly curious. Imagine standing at the edge of the unknown, gazing into the depths of space or the intricacies of a single atom, and realizing that some answers may forever lie just beyond our reach. This is the heart of the uncertainty principle, a concept that reshapes not only how we see the quantum world, but how we understand our very place in the cosmos. It tells us that the act of observation itself changes what we observe, that certainty and precision have their limits, and that the universe operates by rules that defy our everyday intuition. Yet far from being a barrier, this uncertainty invites us into a richer, more nuanced relationship with reality, one where mystery and discovery walk hand in hand. In this video, we're setting out on a journey to explore how this principle shapes not only physics but our perception of existence itself. We'll uncover why the universe seems to guard its deepest truths, how this limitation has driven some of the most revolutionary ideas in science, and what it means for our future as a species striving to comprehend the infinite. This isn't just a story about particles and probabilities. It's about human ambition, wonder, and our endless desire to push beyond the known. So settle in, open your mind, and let's venture together into a world where certainty gives way to curiosity, and where not knowing becomes the very source of discovery. To grasp the uncertainty principle, we first need to travel back to a time of scientific upheaval, to the very dawn of the 20th century. The physics of the day, what we now call classical physics, was a majestic and seemingly complete edifice built by giants like Newton and Maxwell. It was a world of comforting certainty where the universe was viewed as a colossal, predictable clockwork machine. If you could know the position and velocity of every particle, you could, in theory, calculate the entire future of the cosmos. It was a powerful, elegant vision, but it was a vision about to be utterly shattered. The first cracks in this foundation appeared not with a bang, but with a faint glow. Physicists were puzzled by a problem known as black body radiation, essentially, how objects emit light when heated. The equations of classical physics predicted that an ideal object would emit an infinite amount of energy at ultraviolet wavelengths, a nonsensical result dubbed the ultraviolet catastrophe. It was the German physicist Max Planck who, in an act of near desperation in 1900, proposed a radical fix. He suggested that energy is not emitted in a smooth, continuous wave, but in tiny, discrete packets he called quanta. This was a monumental break from tradition, an ad hoc solution that even Planck himself was uneasy with. He had introduced the idea that energy was granular, not smooth, and in doing so, he planted the first seed of a revolution. That seed was soon watered by a young patent clerk in Switzerland. Just 5 years later, Albert Einstein, taking Planck's idea seriously, used it to solve another confounding puzzle, the photoelectric effect. Shining light on a metal surface could knock electrons loose, but classical theory couldn't explain why the color of the light, not its intensity, determined the energy of the ejected electrons. Einstein boldly proposed that light itself was made of particles, packets of energy we now call photons. This wasn't just a wave, it was also a particle. Light had a dual nature, behaving as either a wave or a particle depending on how you looked at it. This wave-particle duality was deeply strange, completely contradicting our everyday experience and the established laws of physics. The next 2 decades became a golden age of bewildering discovery. Niels Bohr proposed a new model of the atom where electrons occupied specific quantized orbits, jumping between them without ever existing in between. Louis de Broglie then turned everything on its head by suggesting that if light waves could act like particles, then perhaps particles like electrons could act like waves. This was soon confirmed experimentally, showing that a beam of electrons could diffract and interfere just like waves of light. The solid, deterministic universe was melting away, replaced by a fuzzy, probabilistic realm where things could be in two places at once, and reality itself seemed to depend on the act of observation. The stage was now set for a young, 25-year-old physicist named Werner Heisenberg to walk into this chaos and provide a mathematical formulation for the inherent weirdness everyone was witnessing. His work would give this new science of the atom its name quantum mechanics and introduce a principle that would forever define its limits. Into this storm of quantum confusion stepped Werner Heisenberg, a brilliant and intensely focused young theorist. While others were trying to visualize electron orbits or reconcile waves with particles, Heisenberg took a radically different approach. He decided to ignore what he couldn't see. He focused purely on the mathematics, on the observable quantities that could be measured in an experiment, like the intensity of light emitted from an atom. This pragmatic, almost austere method led him to develop an entirely new form of mechanics based on matrices, a complex mathematical framework that correctly predicted atomic behavior, but was so abstract it offered no comforting mental picture of what was actually happening inside an atom. This mathematical triumph, however, was merely the prelude to an even deeper insight. In the spring of 1927, seeking relief from a severe bout of hay fever, Heisenberg retreated to a small, Spartan cabin on the bleak, windswept island of Heligoland in the North Sea. The pollen-free air allowed him to breathe and think clearly, and there, surrounded by the stark isolation of the sea, he had a series of profound realizations that would forever change our understanding of reality. He was grappling with a core paradox. In the quantum world, concepts like the precise position and momentum of a particle seemed to lose their meaning. How could you talk about an electron being in a specific place with a specific speed if the very act of looking at it fundamentally changed it? His breakthrough came in the form of a brilliant thought experiment, now famously known as the gamma-ray microscope. He asked a simple operational question: how would you actually measure the position of something as tiny as an electron? To see any object, you need to illuminate it with light. But light comes in packets photons, and each photon carries a kick of energy and momentum. To pinpoint the location of an electron with extreme precision, you would need to use light with a very short wavelength, like high-energy gamma rays. The shorter the wavelength, the finer the detail you can resolve, just like using a finer brush to paint thinner lines. But here was the catch: a high-energy gamma-ray photon, necessary for such a precise position measurement, would deliver a powerful kick to the electron when it bounced off, like a cue ball smashing into a single billiard ball on a vast, empty table. This interaction would dramatically change the electron's momentum in an unpredictable way. You would know exactly where it was at the moment you looked, but you would have no idea where it was going or how fast. Conversely, if you wanted to gently measure the electron's momentum without disturbing it too much, you would need to use a very low-energy photon with a long wavelength, like a radio wave. But such a long wavelength would give you a terribly fuzzy picture of its location. It would be like trying to find a single grain of sand on a dark beach by waving a giant, fluffy flashlight. You might get a general sense of movement, but you'd have no clue exactly where the grain was. Heisenberg realized this wasn't a limitation of his microscope design. It was a fundamental feature of the universe. The disturbance wasn't an engineering problem to be solved. It was an inescapable consequence of the quantum nature of light and matter. You could never simultaneously know both the exact position and the exact momentum of a quantum particle. The more precisely you pinned down one, the more wildly uncertain the other became. This was the birth of the uncertainty principle. It wasn't a statement about what we don't know yet. It was a statement about what we cannot know, a fundamental limit on knowledge itself woven into the fabric of existence. The universe, it seemed, was built on a foundation of irreducible uncertainty. Heisenberg's gamma-ray microscope thought experiment gives us a powerful way to visualize this trade-off, but to truly appreciate its implications, we need to translate it from a scientific concept into a more familiar language. Think of it not as a subatomic problem, but as an everyday dilemma. Imagine you're in a pitch-black room, and your only tool is a flashlight. Your goal is to track a single, fast-moving mosquito. How would you do it? If you use a tightly focused, high-power beam, a laser pointer, essentially, you can get an incredibly precise snapshot of where the mosquito is at this exact instant. The beam is so narrow and bright that it leaves no doubt about its location. But in that brilliant, fleeting moment of perfect clarity, you've completely blinded yourself to its speed and direction. Was it hovering, zipping left, darting upward? You have no idea because your powerful light only captured a single, frozen point in time. You know exactly where it was, but its momentum is now a complete mystery. Now, let's say you want to understand its flight path. You switch to a wide, soft, diffuse beam, a large lantern that casts a gentle glow across a whole section of the room. In this soft light, you can clearly see the graceful arc of its movement. You can track its speed and get a beautiful sense of its momentum. But the trade-off is immediately apparent. You can no longer say exactly where it is within that large, illuminated area. It's somewhere in that soft glow, but its precise position is fuzzy, uncertain. You've gained perfect knowledge of its motion at the cost of losing all precision about its location. This is the essence of Heisenberg's uncertainty principle for position and momentum. The act of measurement itself forces this choice. The photon of light you use to see the particle is the flashlight beam. A high-energy, short-wavelength photon, your laser pointer, gives you perfect positional knowledge but wildly disrupts the particle's momentum. A low-energy, long-wavelength photon, your lantern, gently reveals the momentum but provides only a blurry, imprecise idea of its location. The crucial point, the one that bends our classical intuition, is that this isn't a flaw in our flashlights. It is not a problem we can engineer our way out of with better technology. This is a fundamental rule of the game. The mosquito itself exists in a state where having a perfectly defined position and a perfectly defined trajectory at the same time is simply not part of reality's design. We can push this analogy even further into the macroscopic world we know. Consider a police officer trying to measure the speed of a car with a radar gun. The radar gun works by firing a beam of electromagnetic waves, essentially photons, at the car and measuring the frequency of the waves that bounce back. This is a fantastically precise way to measure velocity, but could it also tell you the car's exact location? Not with any real precision. The best it can do is tell you the car is somewhere within the wide cone of the radar beam. To get its exact location, you'd need a different tool, like a high-resolution camera taking a photograph. That photograph would give you a pixel-perfect snapshot of its position at a specific nanosecond, but it would tell you absolutely nothing about its speed. You'd have to infer its speed by comparing multiple photographs, but in the space between those snapshots, its velocity could have changed. You can have the perfect speed measurement or the perfect location snapshot, but the laws of physics prevent you from having both with ultimate precision at the exact same time. This is the profound shift in thinking that Heisenberg introduced. In our large-scale world, we assume that a car has both a specific position and a specific speed, and our inability to measure them simultaneously is just a technical limitation. But in the quantum realm, for the electron or the photon, that assumption breaks down. The universe does not allow the particle to possess both exact properties at once. The uncertainty is not in our knowledge, it is in the very nature of the particle's existence. It's not that we are bad experimenters, it's that the particle itself lives in a haze of potential, only settling into a more defined state when we force it to answer a specific question, and in doing so, we make other questions unanswerable. This reveals a cosmos that is not a collection of definite things, but a tapestry of probabilities and relationships, where the questions we choose to ask actively shape the answers we receive. Just as we cannot know both the position and momentum of a particle with absolute certainty, the universe imposes another, even more mind-bending trade-off, this time between energy and time. This form of the uncertainty principle is less intuitive but every bit as revolutionary, and it leads us to one of the most astonishing conclusions in all of modern physics: that empty space is not empty at all. Think of it this way: the energy-time uncertainty principle tells us that the more precisely we want to measure the energy of a system within a specific time interval, the less certain we can be about how much energy is actually there during that fleeting moment. Conversely, if we want to know the exact energy state with perfect precision, we must observe it for an infinitely long time. This isn't about a clumsy measurement technique, it's a fundamental feature of reality. For incredibly short periods, the universe's strict accounting of energy can appear to have a margin of error, a tiny loan that can be taken out and paid back almost instantly. This has a breathtaking consequence for what we call a vacuum. Classically, a vacuum is pure nothingness, a void completely devoid of matter and energy. But quantum mechanics, through the energy-time uncertainty principle, paints a radically different picture. For times so short we cannot possibly measure them, energy can fluctuate, borrowing from the universe itself to spontaneously create something from nothing. These aren't just abstract numbers on a page. This borrowed energy can momentarily coalesce into real particles. Imagine the void as a vast, calm ocean. To our eyes, the surface may seem perfectly flat and still, but if we could zoom in to an unimaginably small scale and for an infinitesimally brief instant, we would see that the surface is actually a seething, bubbling foam. In the same way, what we perceive as empty space is actually a vibrant sea of temporary particles flickering in and out of existence. These are known as virtual particles, and they are a direct result of the energy-time uncertainty principle. A particle and its antiparticle partner can spontaneously emerge from the vacuum, existing for a time so short it is governed by Heisenberg's rule. The more massive the particles, the more energy required to create them, and therefore the shorter their fleeting lives must be. We know this isn't just a mathematical fantasy because we can actually observe its effects. In 1948, the Dutch physicist Hendrik Casimir made a stunning prediction. He envisioned placing two perfectly smooth, uncharged metallic plates extremely close together in a vacuum, separated by a tiny gap. While an infinite variety of virtual particles can pop into existence in the open space outside the plates, only those particles whose wavelengths fit perfectly between the plates can form inside the gap. This means there are simply more virtual particles pushing on the plates from the outside than from the inside. The result: the plates are gently pushed together by the pressure of nothingness itself. This Casimir effect was experimentally confirmed decades later, providing tangible proof that the quantum vacuum is alive with transient activity. This phenomenon scales up to truly cosmic proportions. The most spectacular example might be Hawking radiation, the process by which black holes are theorized to slowly evaporate. Stephen Hawking applied the energy-time uncertainty principle right at the edge of a black hole's event horizon. There he proposed a virtual particle-antiparticle pair could spontaneously form. Normally, these pairs would annihilate each other almost immediately, paying back the energy loan. But if this happens right at the precipice, one particle could fall into the black hole's immense gravity while the other escapes into space. the escaped particle becomes real, carrying energy away from the black hole, which consequently loses a tiny amount of mass. Over eons, this process could cause a black hole to completely evaporate. This means the ultimate engines of cosmic destruction are themselves slowly being undone by the restless quantum fluctuations of empty space. So this second form of uncertainty is not a minor footnote. It completely rewrites our definition of nothing. It tells us that the vacuum is a dynamic, bubbling canvas upon which all of reality is painted. These quantum fluctuations were likely the primordial seeds from which the entire large-scale structure of our universe, the vast cosmic web of galaxies and galaxy clusters, first grew. From the unimaginably small to the cosmically vast, the uncertainty between energy and time is a fundamental creative force, proving that the universe's inherent ambiguity is not a barrier to knowledge, but the very source of its infinite complexity and beauty. This leads us to a crucial point of clarification, one that often gets tangled in popular science discussions. It's incredibly easy to confuse Heisenberg's uncertainty principle with something called the observer effect. While they are related, they are not the same thing, and understanding this distinction is key to moving from a superficial to a profound appreciation of quantum mechanics. The observer effect is a concept we encounter in our everyday macroscopic world. It's the simple idea that the act of measuring a system can inevitably disturb it. If you use a thermometer to check the temperature of a cup of water, the thermometer itself must absorb a tiny amount of heat from the water to give a reading, thereby slightly cooling the water in the process. You haven't measured the original temperature perfectly because your tool changed it. This is a practical limitation, and in theory, with a perfect, infinitely sensitive instrument, you could minimize this disturbance until it becomes negligible. For a long time, physicists assumed the uncertainty in the quantum world was just a supercharged version of this, a technological hurdle we might one day overcome with better, gentler microscopes. But Heisenberg's principle is something far deeper and more unsettling. It is not about the clumsiness of our tools, it is about the inherent nature of what we are trying to measure. The core of the issue lies in the bizarre wave-particle duality we discussed earlier. An electron is not a tiny, hard marble that has a definite position and a definite momentum that we are simply too rough to measure without disturbing. Instead, according to quantum theory, the electron does not possess exact values for these properties simultaneously until an act of measurement forces it to choose. Think of it not as a particle with hidden properties, but as a spread-out wave of potential, a probability wave. This wave describes all the possible positions the electron could be found in and all the possible momenta it could have all at once. It exists in a blurred state of superposition. The moment we perform a measurement to ask it a specific question like, "Where are you right now?" this probability wave collapses. It picks a single, definite answer from the menu of possibilities. However, by forcing it to give a precise answer about its location, we lose all the detailed information about its momentum that was encoded in the wave. The uncertainty is baked into the very recipe of a quantum object's existence. It's not that we are shaking the electron too much when we look at it. It's that the electron's reality is fundamentally fuzzy until we interact with it. This is why the idea of a passive observer is a myth in quantum mechanics. The measurement isn't a passive reading of pre-existing data. It is an active intervention that fundamentally changes the system, compelling it to take a specific form. The particle doesn't have a well-defined trajectory before we measure it. Our choice of what to measure, whether to ask the "where" question or the "how fast" question, literally sculpts the reality we then observe. This profound distinction transforms the uncertainty principle from a frustrating limit on our knowledge into a breathtaking window into the nature of reality itself. It tells us that the universe at its most fundamental level is not a collection of tiny, independent billiard balls. It is a vast, interconnected network of potentialities and relationships where properties are not inherent but are rather defined through interaction. This isn't a statement about what we can't know because our tools are too big. It's a statement about what isn't there to be known until the moment we look. Perhaps the most incredible thing about all this quantum strangeness is that it isn't confined to thought experiments or physics laboratories. It's not some abstract philosophical puzzle. The bizarre rules of the quantum world, including the uncertainty principle and wave-particle duality, are the very engine of our modern technological reality. They are humming away inside the devices that define our lives, proving that this fundamental uncertainty isn't a barrier to progress, it's the source of our most powerful innovations. Let's start with a technology that saves countless lives every day, the magnetic resonance imaging machine, or MRI. If you were to lie inside one of these devices, you'd be placed in an immensely powerful magnetic field. This field does something extraordinary to the atoms in your body, particularly the hydrogen atoms abundant in water and fat. The nuclei of these atoms act like tiny spinning tops, and the magnetic field causes most of them to align with it. But here's where quantum mechanics takes the wheel. These atomic nuclei can't just align in any old way. Their spin is quantized. Thanks to the principles born from the same revolution that gave us uncertainty, these spins can only exist in one of two discrete states, often thought of as spin up or spin down. The machine then pulses the area with a specific frequency of radio waves. This is the magic bullet. This precise frequency provides exactly the right amount of energy to flip the spin of these hydrogen nuclei from one state to the other, a quantum leap that is only possible because energy levels are quantized. When the radio wave pulse stops, the nuclei relax back to their original alignment, and in doing so, they release their own faint radio signal. The uncertainty principle is subtly at play here too. The incredibly short time it takes for these nuclei to relax means there's a fundamental uncertainty in the energy they emit, which actually helps create the detailed contrast between different types of tissue. A computer translates all these signals into an exquisitely detailed image of your soft tissues, allowing doctors to see things like torn ligaments or tumors. An MRI doesn't take a picture of your body, it listens to the quantum songs of your atoms and translates them into a diagnosis. Then there's the laser, a technology so common we point them at walls during presentations and use them to scan our groceries. The word laser itself is an acronym for light amplification by stimulated emission of radiation, and every part of that name is steeped in quantum mechanics. Stimulated emission, the core process, was first described by Einstein. It relies on electrons occupying specific, quantized energy levels within atoms. When an electron in a high energy state is struck by a passing photon, it can be stimulated to drop down to a lower energy level, emitting a second photon that is perfectly identical to the first in every way, same wavelength, same direction, same phase. This process creates a cascade of identical photons, a coherent beam of light where all the waves are marching in lockstep. This is utterly unlike the scattered, jumbled light from a light bulb. But why does this work so well? It works because of the Pauli exclusion principle, another quantum rule that says no two electrons can occupy the exact same quantum state. This forces the atoms in the laser material to organize their electrons into distinct energy levels, creating the perfect conditions for this coordinated light emission to occur. The precise, single-color, focused beam of a laser used in everything from eye surgery and manufacturing to fiber optic internet and DVD players is a direct and powerful manifestation of the quantum world's discrete rules. And we cannot forget the transistor, the fundamental building block of every single microchip that powers our computers, phones, and the internet itself. A transistor is essentially a tiny switch that controls the flow of electrical current. The first point contact transistor, invented in 1947, was a crude device, but it unlocked a revolution. It worked by leveraging the weird properties of semiconductors like silicon. In a semiconductor, the behavior of electrons is governed by quantum mechanics. They don't move freely like they do in a metal. Instead, they exist in specific energy bands. The crucial region is the band gap, a forbidden energy zone that electrons cannot occupy, a concept that is purely quantum. By adding tiny impurities, a process called doping, engineers can create regions where there are extra electrons or extra holes where electrons can go. When you bring these different semiconductor regions together, you create a junction where quantum mechanical tunneling and the movement of charge carriers can be precisely controlled by applying a small voltage. This allows a tiny signal to control a much larger one, enabling both amplification and switching. This quantum-controlled switch, manufactured by the billions on a sliver of silicon, is the heart of the digital age. Without the quantum behavior of electrons in semiconductors, there would be no processors, no memory, and no information age as we know it. So the next time you get a detailed medical scan, use a barcode scanner or check your phone, remember you are holding the products of quantum uncertainty. These aren't technologies that merely work despite the weirdness of the quantum world. They work because of it. They are practical, tangible proof that accepting the universe's fundamental ambiguities doesn't limit us. It unlocks a new frontier of potential, turning the paradoxical into the powerful. Yet this intimate dance of uncertainty isn't confined to the infinitesimally small. Its implications ripple outward, scaling up to shape our very view of the cosmos. When we train our most powerful telescopes on the faintest, most distant galaxies, we are essentially performing a measurement on a colossal scale, and the uncertainty principle is right there with us, imposing fundamental limits on what we can ultimately know. It whispers that there is a cosmic horizon to precision, a point beyond which the universe itself prevents a clearer picture. Consider the immense challenge of measuring the properties of a galaxy billions of light years away. We want to know its exact position, its velocity, the distribution of its dark matter halo. To pinpoint its location with incredible accuracy, we need to collect as many photons as possible, using long exposure times on giant mirrors. But here, the uncertainty principle manifests not through a photon's kick, but through the wave nature of light itself. The light from that galaxy is not a perfectly sharp signal, it's a wave spread out in space. The more precisely we try to measure its position on the sky, by using a larger telescope aperture to better resolve its angular size, the more we run into the diffraction limit, a direct cousin of the uncertainty principle. We are trading precise positional knowledge for an uncertainty in the direction of the incoming light waves. This isn't a blurry image because our optics are bad. It's a fundamental limit imposed by the wavelength of light and the size of our telescope. We cannot build a perfect lens that violates this quantum rule. This plays out dramatically in our quest to map the mysterious dark matter that makes up most of the universe's mass. We can't see dark matter directly, so we infer its presence and distribution by observing how its gravity bends the light from background galaxies, an effect called gravitational lensing. The precision of this cosmic map is paramount, but the light from those background galaxies is not a pristine, undistorted signal. It has been slightly scrambled by the very quantum uncertainty it was born from. Furthermore, the act of measuring the faint, distorted shapes of these galaxies is itself a quantum-limited process, as we are counting discrete photons arriving at our detector. There is a fundamental, statistical noise inherent in this photon count that we can never overcome, a direct result of the particle nature of light. This means the map of dark matter we painstakingly assemble will always have an inherent graininess, a fundamental fuzziness written into it by the laws of quantum mechanics. Our view of the cosmos's largest structures is forever filtered through the quantum uncertainty of its smallest particles. Perhaps the most profound application lies at the very beginning of everything. Cosmologists believe that the entire universe we see today, hundreds of billions of galaxies, expanded from a region smaller than a single atom in a rapid event called inflation. In this unimaginably dense and energetic state, the universe was a quantum system. The energy-time uncertainty principle would have been the dominant force, allowing wild fluctuations in energy to spontaneously occur. These microscopic quantum fluctuations, these temporary bubbles of somethingness in the newborn void, were not smoothed away. Instead, the rapid expansion of inflation stretched them to astronomical sizes, freezing them into the fabric of space-time itself. Those random quantum jitters became the seeds for all future structure. The slightly denser regions where a tiny bit more matter flickered into existence thanks to uncertainty, eventually collapsed under gravity to form the first galaxies and clusters. This means the entire cosmic web we see today, the vast, intricate filamentary structure of galaxies surrounding great empty voids, is essentially a quantum pattern writ large across the sky. The uncertainty principle is not a limitation here, it was the creative engine. Without it, the early universe would have been too smooth, too uniform, and galaxies might never have formed at all. Our very existence hinges on this primordial uncertainty, yet this glorious origin story also places a hard limit on our knowledge. We can look back to a point very close to the Big Bang, but we can never peer all the way back to time zero itself. The energy scales and time scales become so extreme that quantum fluctuations would have been overwhelming, blurring the very concepts of space and time into a foamy, chaotic broth where our current laws of physics break down. The uncertainty principle draws a final veil over the universe's absolute beginning, protecting its deepest secret. It tells us we can trace the story back to a phenomenal degree, but the first page of the book may forever be unreadable, a permanent testament to the fact that some truths are fundamentally unknowable. This brings us to one of the most profound clashes between quantum mechanics and gravity, a puzzle born directly from the quantum uncertainty of the vacuum and centered on the most enigmatic objects in the cosmos, black holes. For decades, these gravitational monsters were thought to be the ultimate vaults, cosmic penitentiaries from which nothing, not even light, could ever escape. Their event horizons marked a one-way door into oblivion, a point of no return where the known laws of physics seemed to break down. But then, Stephen Hawking made a startling calculation that turned this simple picture on its head, and the key that unlocked this revolution was the energy-time uncertainty principle and its bubbling sea of virtual particles. Hawking asked a deceptively simple question: what happens to the quantum vacuum at the very edge of a black hole's event horizon? We know that empty space is not truly empty. It's a seething foam of virtual particle-antiparticle pairs constantly flickering in and out of existence, borrowing energy from the universe before annihilating and paying it back almost instantly. Now, imagine this process happening not in the calm of flat space, but right on the precipice of a black hole's immense gravitational field. Hawking realized that the gravitational energy at the horizon could profoundly disrupt this delicate dance. In this extreme environment, a virtual particle pair could pop into existence right at the edge. Normally, they would recombine and vanish in a fleeting instant. But the black hole's immense gravity can intervene. In a fraction of that unimaginably short time, one particle of the pair might fall across the event horizon, while the other is propelled outward, escaping into space. The particle that falls in carries negative energy with it, which effectively reduces the black hole's mass by a tiny amount. Its partner, now severed and unable to annihilate, becomes a real particle, carrying positive energy away from the black hole. To an outside observer, it appears as if the black hole itself is emitting a faint glow of radiation. This is Hawking radiation, a slow, steady leak of energy directly caused by quantum uncertainty at the frontier of spacetime. This was a breathtaking result. It meant black holes are not eternal. They slowly evaporate, losing mass over astronomical timescales until they potentially vanish entirely. But this beautiful solution created a monstrous new problem, one that has haunted theoretical physics for half a century: the information paradox. According to Hawking's original calculation, the radiation being emitted is purely thermal. It's random noise, like the heat radiating from a stove, containing no specific information about what fell into the black hole. Whether you threw in a perfect diamond, a library of books, or a cloud of hydrogen, the Hawking radiation would look exactly the same. It only depends on the black hole's mass, charge, and spin. This presents a fundamental crisis for physics. Quantum mechanics is built on the principle of unitarity, which essentially means that information is never truly lost. The universe is like a perfect, eternal accountant. It must always be possible, in principle, to reverse the clock and reconstruct the past from the present. If you burn a book, the information isn't truly gone. It's just fantastically scrambled into the arrangement of the ash and the light and heat that were released. But Hawking's calculation suggested that when a black hole evaporates completely, all the detailed information about everything it ever consumed is irretrievably erased from the universe. The cosmic accountant's ledger is not just scorched, it's blank. This violates a core tenet of quantum theory and creates a deep, irreconcilable conflict with Einstein's general relativity, which governs the black hole itself. The physics community was split. Hawking himself famously argued for years that information was indeed lost, a stance that led to a famous bet with other physicists who believed information must be preserved. The paradox forced physicists to question the very foundations of their understanding, suggesting that our theories of the very large and the very small are fundamentally incompatible at this precipice. Resolving it would require something new, a deeper theory that could unite quantum mechanics and gravity, perhaps through string theory or loop quantum gravity, or a radically new idea like the holographic principle, which suggests that all the information contained within a volume of space might actually be encoded on its two-dimensional boundary like a cosmic hologram. The event horizon, in this view, becomes a screen onto which the information of infalling objects is projected and preserved, eventually encoded into the Hawking radiation itself as the black hole evaporates. The story of the information paradox is far from over. It remains one of the most active and contentious frontiers of theoretical physics. It stands as a powerful testament to how a concept born from the uncertainty of the microscopic vacuum can scale up to challenge our most fundamental ideas about reality, causality, and the preservation of the cosmic story itself. It shows us that the universe's deepest secrets are not just hidden in the distant past or the far reaches of space, but are woven into the paradoxical nature of its most extreme phenomena. If the uncertainty principle and its strange rules seem like a frustrating barrier to knowledge, then prepare for a beautiful twist. We are now learning to not just accept this quantum fuzziness, but to actively harness it as the most powerful computational resource ever conceived. This is the frontier of quantum computing, a field that doesn't fight the inherent uncertainty of the quantum world, but instead recruits it, turning what was once a limitation into its greatest strength. At its heart is a radical departure from everything we know about information, replacing the definitive binary world of ones and zeros with a fluid, probabilistic realm of simultaneous possibilities. To understand this quantum leap, let's first look at the foundation of all our current technology, the classical bit. A classical bit is the smallest unit of digital information, and it is profoundly simple. It can be in one of two distinct states, represented as a 0 or a 1. It's like a standard light switch. It's either definitively on or definitively off. Every email you send, every song you stream, every calculation performed by the most powerful supercomputer on Earth is at its core a colossal tapestry of billions upon billions of these simple, deterministic bits flipping on and off in a precisely orchestrated sequence. This paradigm has served us incredibly well, but it hits a fundamental wall when faced with certain types of problems that are exponentially complex. A quantum computer operates on an entirely different principle, using quantum bits or qubits. Unlike its classical cousin, a qubit is not a light switch. It's more like a dimmer knob that can be set to any point on a sphere of possibility. Thanks to the quantum principle of superposition, a qubit can be in a state of 0 and 1 simultaneously. It's not that we don't know which state it's in. It genuinely exists in a blend of both until we measure it, at which point the probability wave collapses and it chooses one state. This means that a single qubit can hold two potential values at once. Two qubits can represent four possible states simultaneously: 0, 0, 0, 1, 10, and 11. Three qubits can represent 8 states. The power grows exponentially. With just 300 qubits, a quantum computer could, in theory, be in a superposition of more states than there are atoms in the known universe. This allows it to explore a near-infinite number of possibilities in parallel, performing a single calculation that would require a classical computer the size of a galaxy to simulate. But superposition is only half the story. The other crucial quantum ingredient is entanglement, a phenomenon Einstein famously called spooky action at a distance. When qubits become entangled, they form a deep, intimate connection that transcends physical separation. The state of one qubit instantly influences the state of its partner, no matter how far apart they are. This isn't just a correlation, it's a fundamental linking of their fates. This allows a quantum computer to perform operations on all those superposed states at once, weaving their probabilities together into a coordinated symphony of computation. The computer manipulates these entangled probabilities, amplifying the pathways that lead to the correct answer and canceling out those that lead to wrong answers, before finally making a measurement to reveal the solution. This unique approach makes quantum computers ideally suited for problems that involve searching vast, unstructured possibilities or modeling complex, multi-variable systems. One of the most talked about applications is in cryptography. Much of our modern digital security, from online banking to secure messaging, relies on the fact that it is computationally infeasible for a classical computer to factor the product of two very large prime numbers. It could take a classical supercomputer thousands of years to crack a modern encryption key through brute force. A sufficiently powerful quantum computer, running a specialized algorithm developed by Peter Shaw, could theoretically solve this problem in a matter of hours or days, rendering current encryption methods obsolete. This isn't a distant threat. It's a driving force behind the development of a new field called post-quantum cryptography, which aims to create new encryption systems that even quantum machines cannot break. Perhaps an even more profound application lies in the realm of chemistry and medicine. Modeling a single molecule is an incredibly complex task for a classical computer because it requires simulating the quantum behavior of every single electron interacting with every atomic nucleus. The number of interactions quickly becomes impossible to calculate precisely. This is why drug discovery and materials science often rely on lengthy trial and error in a lab. A quantum computer, however, operates by the same quantum rules as the molecule itself. It doesn't have to simulate the quantum behavior, it can embody it. We could use qubits to directly represent the electrons in a molecule, allowing us to model and predict with incredible accuracy how a potential drug will interact with a protein, or how to design a new material with bespoke properties, like a room temperature superconductor or a more efficient battery catalyst. This could dramatically accelerate the development of life-saving medicines and transformative technologies, tackling problems we simply cannot solve with any amount of classical computing power. It's a thrilling prospect, but building a practical quantum computer is perhaps the hardest engineering challenge humanity has ever undertaken. Qubits are incredibly fragile. Any tiny interaction with the outside environment, a stray photon, a vibration, or even a cosmic ray, can cause them to lose their delicate superposition in a process called decoherence, effectively collapsing the computation into a random error. Maintaining qubits in their quantum state requires isolating them at temperatures colder than deep space and shielding them from all external noise. The machines themselves are often breathtaking works of engineering, vast, intricate chandeliers of gold and copper plumbing designed to cool a processor chip down to a fraction of a degree above absolute zero. Despite these immense challenges, progress is accelerating. Companies and research institutions are now demonstrating quantum processors with hundreds of qubits, and while full-scale, error-corrected quantum computers are still on the horizon, they represent a new computational paradigm born directly from our embrace of the universe's inherent uncertainty. Yet the story doesn't end with the practical applications of quantum mechanics. It spirals out into one of the most audacious and mind-bending interpretations of what this inherent uncertainty might truly mean for the nature of reality itself. If a quantum particle exists in a blur of probabilities until it is measured, what exactly constitutes a measurement, and what happens to all those possibilities that we don't observe? One radical answer, born directly from wrestling with these questions, suggests that they are all realized, just not in our universe. This is the many worlds interpretation, a theory that uses quantum uncertainty not as a barrier, but as a doorway to a multiverse of infinite branching realities. The problem it seeks to solve is known as the measurement paradox. In the standard Copenhagen interpretation of quantum mechanics, the act of observation by a conscious observer causes the probability wave to collapse into a single definite outcome. But this has always raised deeply uncomfortable questions. What qualifies as an observer is a cat in a box conscious enough, a photon detector, a single atom. This introduces a strange divide between the quantum world, which behaves probabilistically, and the classical world of measurement devices, which seems definite. The many worlds interpretation, first proposed by Hugh Everett in 1957, offers a starkly elegant and utterly bizarre alternative. There is no collapse. The probability wave never collapses at all. Instead, Everett suggested that every time a quantum system faces a probabilistic choice, like an electron being spun up or down, or a photon being reflected or transmitted, the entire universe effectively splits. In one branch, the observer measures the electron as spin up. In another, perfectly real branch, a different version of that same observer measures the electron as spin down. Both outcomes happen. There is no single privileged outcome. The entire cosmos undergoes a continual process of branching, creating a vast, ever-expanding tree of parallel universes where every possible quantum event is realized somewhere. In this view, the uncertainty principle doesn't tell us what we can't know. It simply reveals the menu of options from which reality continuously selects by multiplying itself. This isn't a theory built on whimsy. It's a mathematically consistent formulation that removes the need for an arbitrary collapse postulate. It treats the entire universe as a single giant quantum wave function that evolves smoothly and deterministically according to Schrödinger's equation. The weirdness we perceive is simply our subjective experience within one branch of this unimaginably complex wave. We don't feel ourselves splitting because our conscious awareness becomes entangled with the specific branch we are in. We follow one timeline, unaware of the countless other versions of ourselves living out the alternatives in other, causally disconnected universes. The philosophical implications are, to put it mildly, staggering. It suggests a reality of truly cosmic proportions, where every choice, every chance event, every random quantum fluctuation spawns new worlds. There is a universe where you never watched this video, and one where you decided to have a different breakfast this morning, and one where the dinosaurs never went extinct. It transforms the concept of probability from a measure of ignorance into a measure of how many branches contain a particular version of you. When you flip a quantum coin, it's not that you have a 50% chance of heads, it's that you will certainly experience both outcomes, just in different branches of the multiverse. But does this truly resolve the paradox, or does it simply exchange one set of philosophical headaches for another? critics point to the breathtaking ontological extravagance of the theory, the sheer, unbelievable number of universes it proposes. It seems to violate Occam's razor, the principle that simpler explanations are generally better, by populating reality with an infinite number of unobservable worlds. Proponents counter that it is actually the simpler theory in terms of its fundamental assumptions, as it requires no special rules for measurement or collapse. It just has one rule that always applies. The complexity is in the outcomes, not the laws. A deeper issue is the problem of probability itself. If every outcome happens in some branch, what does it mean to say that a particular outcome has a 90% probability? In what sense is it more likely? Everett's answer lies in the measure of branches. A high probability outcome doesn't happen in more branches, but rather, the branches where it happens have a greater weight or amplitude in the wave function. But translating this abstract mathematical weight into our subjective experience of chance remains a significant challenge for the interpretation. Ultimately, the many worlds interpretation is a powerful testament to how far the logic of quantum mechanics can be pushed. It shows that our attempts to make sense of the universe's fundamental uncertainty can lead us to places far stranger than we ever imagined. Whether it is the true description of reality or a fascinating intellectual detour, it forces us to confront the sheer scale of what might be possible, transforming the quantum fuzziness at the heart of things from a limitation into a generative engine for endless realities. This profound shift from a universe of definite objects to a universe of potentialities and relationships forces us to confront one of the most disorienting questions in all of science: what is real? If the properties of a particle aren't defined until we measure them, can we truly say an objective reality exists independently of our observation? This isn't just physics. It's a deep philosophical chasm that divided the very founders of quantum mechanics, pitting two of the greatest minds of the 20th century against each other in a debate about the fundamental nature of existence. On one side stood Niels Bohr and his Copenhagen interpretation, which became the orthodox view for much of the physics community. For Bohr, the uncertainty principle wasn't a limitation, it was the final word. He argued that it is meaningless to talk about what a quantum particle is really doing when we're not looking. An electron does not have a definite position or momentum. Those properties only come into being through our interaction with it. In his view, the particle's wave function isn't just a description of our knowledge, it is the complete description of the system. The act of measurement isn't a passive recording but an active intervention that forces the system to choose a specific reality from a menu of possibilities. This perspective suggests that reality is, in a very deep sense, participatory. We are not detached observers of a pre-existing cosmic play. We are actors on the stage, and our entrances and exits influence the plot itself. Bohr famously insisted that if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. His interpretation demands we let go of our classical, intuitive yearning for a single, objective world and accept a universe that is fundamentally fuzzy and relational at its core. Arrayed against this radical view was none other than Albert Einstein, who found the implications of the Copenhagen interpretation deeply unsatisfactory, even distasteful. While he was instrumental in founding quantum theory, he could not accept a universe governed by fundamental chance and observer-dependent reality. His famous objection, "God does not play dice with the universe," was not a throwaway line but a profound statement of his belief in a deterministic cosmos, where things happen for a reason and objects have properties whether we look at them or not. For Einstein, the uncertainty principle wasn't a description of reality's nature but a sign that the theory was incomplete. He believed there must be hidden variables, deeper, as yet unknown properties, that determine a particle's behavior with perfect certainty, restoring a sense of classical order and objectivity to the quantum realm. He aimed to prove this through a series of clever thought experiments designed with his colleagues Boris Podolsky and Nathan Rosen. arguments meant to show that quantum mechanics must be an incomplete description of reality. This intellectual clash culminated in the famous EPR paradox, which argued that if quantum mechanics were correct and complete, it would lead to spooky action at a distance, seemingly instantaneous connections between particles that violated the speed of light, a cornerstone of his own theory of relativity. Einstein believed this was so absurd it proved his point. For decades, this remained a philosophical debate, a war of ideas fought with thought experiments and mathematical formalism. But then, decades later, a physicist named John Bell devised a real, testable experiment that could decide the issue. When those experiments were finally performed, the results were unequivocal. The universe agreed with Bauer and the spooky action. Quantum entanglement was real, and there were no local hidden variables. Reality, it seemed, was indeed non-local and deeply strange, leaving Einstein's dream of a perfectly deterministic cosmos behind. This leaves us in a fascinating, if unsettling, position. The universe appears to be objectively probabilistic, not because of our ignorance, but because of its inherent design. The quest for a single, observer-independent reality may be a relic of our classical intuition, a comforting story we tell ourselves that doesn't hold up under the harsh, brilliant light of experimental scrutiny. We are left with a cosmos that is not a collection of things, but a web of interactions and potentials where the act of questioning is inextricably linked to the answer received. This doesn't make reality any less real. It makes it far more mysterious, complex, and wondrous, inviting us into a much more nuanced and participatory relationship with the cosmos we are trying to understand. For decades, biology was considered the domain of the classical, a world far too warm, wet, and messy for the delicate dance of quantum coherence to survive. How could a phenomenon that requires near-total isolation and freezing cold to be observed in a lab possibly play a role in the chaotic environment of a living cell? It seemed an impossible frontier, yet astonishingly, that is precisely where the evidence is now pointing. The razor-sharp line between the quantum and classical worlds is blurring, and life itself appears to be a masterful quantum engineer, harnessing the power of uncertainty and superposition to perform feats of efficiency that our best technology can only dream of. One of the most stunning and well-documented examples is in the very foundation of life on Earth, photosynthesis. Inside the cells of plants, algae, and some bacteria are intricate structures called photosynthetic complexes. Their job is to capture photons of sunlight and funnel that energy to a reaction center where it can be converted into chemical fuel. For a long time, we thought this process was a straightforward, if efficient, random walk. The energy from an absorbed photon, called an exciton, would bounce around like a pinball through the forest of chlorophyll molecules until it, by chance, found its target. This should be a relatively slow and lossy process with much of the energy wasted as heat, but that's not what happens. The transfer is almost 100% efficient. The mystery of how this was possible began to unravel when scientists started applying the principles of quantum mechanics. They discovered that the exciton doesn't take a single path. Instead, it exploits quantum superposition to effectively explore all possible pathways through the complex simultaneously. It's as if the energy is a wave spreading out across a pond, testing every route at once, and then collapsing onto the most direct and efficient path to the reaction center. This quantum coherent walk allows the energy to find its target with near-perfect efficiency before the fragile quantum state has a chance to decohere and be destroyed by the noisy cellular environment. Life isn't just tolerating quantum effects, it is actively maintaining and utilizing them to outperform any classical process. This quantum ingenuity isn't confined to the plant kingdom. Consider the humble European robin, a bird that migrates thousands of miles with pinpoint accuracy. How does it navigate so precisely, especially on overcast nights when visual landmarks are unavailable? The leading theory points to a quantum compass inside its eye. The hypothesis involves a protein called cryptochrome. When a photon of light hits this protein, it can kick off a chemical reaction that creates a pair of molecules with unpaired electrons. These electrons are quantum entangled, their spins intimately linked. The Earth's faint magnetic field exerts a slightly different influence on each of the molecules depending on their orientation relative to the field. This tiny quantum-level effect changes the chemical state of the protein. It is believed the bird can literally see the Earth's magnetic field as a subtle visual pattern overlaying its vision, a compass painted directly onto the world by the quantum spin of entangled electrons. This is a sensory mechanism built not on classical magnetism, like a needle on a compass, but on the spooky, non-local connection of quantum entanglement, allowing the bird to perceive a fundamental force of nature in a way we can scarcely imagine. These discoveries in biology inevitably lead to one of the most speculative and fascinating frontiers of all, the human brain and the nature of consciousness itself. Could the mystery of subjective experience, our thoughts, feelings, and awareness be rooted in the quantum world? This is the provocative proposal of theories like orchestrated objective reduction, put forward by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their theory suggests that the fundamental seat of consciousness isn't the neuron itself, but structures within neurons called microtubules. These tiny protein polymers form the cytoskeleton, the scaffolding of our cells. Penrose and Hameroff propose that these microtubules are perfectly structured to protect and process quantum information. They suggest that within these structures, quantum superpositions can form and be maintained. Consciousness, in this view, arises at the moment these quantum superpositions collapse, not through a random environmental disturbance, but through a proposed objective process Penrose links to the very foundations of spacetime geometry. In this model, each moment of conscious experience is a discrete quantum event. It's a breathtakingly ambitious idea that attempts to bridge the gap between the physics of the very small and the most intimate aspect of our human experience. Unsurprisingly, this theory is met with significant skepticism. The brain is widely considered the ultimate warm, wet, and noisy environment, seemingly the worst possible place for large-scale quantum coherence to occur. Critics argue that the timescales involved in neural processes are far too slow, and the systems far too disruptive for such delicate quantum states to play a functional role. The mainstream view in neuroscience remains that consciousness is an emergent phenomenon of complex classical computation among neural networks, yet the door is not completely closed. The discovery of quantum effects in photosynthesis and bird navigation proves that biology can indeed exploit the quantum realm, even in seemingly hostile environments. This has opened a new field of quantum biology, forcing us to ask not if but how and to what extent life utilizes these phenomena. Whether quantum processes are the source of consciousness or merely another ingenious tool in life's ancient toolkit, their presence in biological systems is undeniable. It suggests that the uncertainty principle is not a barrier life encounters, but a resource it has learned to harness, weaving the fundamental fuzziness of the quantum world into the very fabric of its being, from the green leaf to the navigating bird, and perhaps even into the depths of our own mind. Yet this inherent quantum fuzziness doesn't just live in theory. It manifests as a tangible, physical barrier that confronts scientists and engineers pushing the very boundaries of measurement. The quest to see deeper into reality demands instruments of almost unimaginable precision, machines so colossal and delicate that they represent the pinnacle of human ingenuity. But no matter how brilliant our engineering, we are forever building against the grain of the universe itself, facing limitations set not by our technology, but by the fundamental laws woven into space-time. Consider the monumental effort behind the Large Hadron Collider, the world's most powerful particle accelerator. This isn't just a machine, It's a 27-kilometer ring of subterranean cathedral, a triumph of engineering designed to accelerate protons to 99.9999991% of the speed of light. To make these particles collide, physicists must focus their beams down to a width thinner than a human hair. Guiding these infinitesimal specks requires magnets cooled by liquid helium to temperatures colder than outer space, creating magnetic fields so precise and powerful they can bend the path of a proton moving at near light speed. The detectors that then record these collisions are equally staggering. Layered devices the size of apartment buildings, packed with millions of sensitive channels that must precisely track the spray of particles born from a collision event that lasts less than a trillionth of a billionth of a second. The engineering challenges are Herculean, involving unprecedented vacuums to prevent protons from hitting air molecules, and a synchrony so exact that firing the proton beams is like firing two needles from across the Atlantic Ocean and making them collide mid-ocean. We build these behemoths to probe shorter distances and higher energies, to glimpse the universe closer to the moment of the Big Bang. But here, the uncertainty principle reasserts its ultimate authority. To probe smaller scales, we need to use higher energy particles. This is a direct consequence of the principle's trade-off. Remember, a high-energy photon has a very short wavelength which is necessary to resolve tiny structures. But that high-energy probe delivers a tremendous kick to whatever it is we're trying to measure. It's the gamma-ray microscope thought experiment scaled up to astronomical proportions. The more violently we smash particles together to see the fine details of their structure, the more we fundamentally disturb the very system we're trying to observe. The LHC isn't just looking at the Higgs boson. Its tremendous energy is creating it, and in that violent act of creation, the precise properties of the particle are inherently uncertain. We can measure its mass, but other properties remain fuzzy, not because our detectors are poor, but because the universe imposes a fundamental limit on the precision we can achieve at those energy scales. Building a next-generation collider, even one 100 kilometers long, would grant us more precision, but it would never grant us infinite precision. The uncertainty principle ensures there is always a final, uncrossable horizon. This push against quantum limits isn't confined to giant machines. It's also the driving force behind the most sensitive sensors ever built. The field of quantum metrology doesn't try to fight uncertainty. It seeks to cleverly work within its rules to achieve the absolute maximum precision allowed by physics. Take the example of gravitational wave observatories like LIGO. These instruments must measure changes in distance 10,000 times smaller than the diameter of a proton. To do this, they use lasers bounced between mirrors suspended 4 kilometers apart. At this scale, the quantum nature of light itself becomes the primary source of noise. The random arrival of individual photons at the detector, a manifestation of quantum uncertainty, creates a constant background hiss called shot noise. Furthermore, the radiation pressure of those very photons constantly bouncing off the mirrors gives them tiny, random kicks, another uncertainty-driven effect called quantum radiation pressure noise. These are not engineering flaws that can be removed with better optics or quieter electronics. They are fundamental features of a quantum universe. The act of measuring the mirror's position with laser light is inherently disruptive. To push past this, scientists are now turning to quantum squeezing, a technique that manipulates the uncertainty principle itself. By using specially prepared quantum states of light, they can effectively reduce the uncertainty in one variable, say, the phase of the light wave, which is used to measure the mirror's position, at the expense of increasing the uncertainty in another, less important variable like the light's amplitude. It's a brilliant end run around the rule, not breaking it but bending it to our advantage, redistributing the fuzziness to where it matters least for the measurement at hand. This is the new frontier of measurement, not building bigger but building smarter. using the strange rules of the quantum world as the very tools to peer just a little deeper into the dark. This same cosmic stubbornness, this fundamental refusal to yield perfect knowledge, is now the very obstacle confronting our most ambitious efforts to listen to the universe itself. The monumental detection of gravitational waves, the ripples in spacetime predicted by Einstein, was one of humanity's greatest scientific achievements. But to hear the faintest whispers of the cosmos, like the collision of the most distant black holes, we must push our instruments into a realm where the universe itself begins to drown out the signal with the inherent noise of existence. This noise isn't a technical flaw, it is the sound of quantum uncertainty imposing its ultimate limit on what we can measure. At the heart of this struggle are observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory. These are not telescopes in any conventional sense. They are the most precise rulers ever built. Each observatory consists of two immense arms, each 4 kilometers long, arranged in a giant L shape. Inside these vacuum pipes, a powerful laser beam is split and sent down each arm, bouncing between near-perfect mirrors suspended at the ends. The beams then travel back and recombine. Normally, the light waves are perfectly aligned to cancel each other out, and the detector sees darkness. But when a gravitational wave passes through Earth, it literally stretches and squeezes spacetime itself. One arm gets infinitesimally longer while the other gets shorter, changing the distance the light travels by an amount thousands of times smaller than the width of a single proton. This minute change disrupts the perfect cancellation of the laser light, allowing a tiny, fleeting signal of light to reach the sensor, the signature of a cosmic catastrophe that happened millions or even billions of light years away. The engineering behind this is almost beyond comprehension. The mirrors are suspended with such exquisite isolation that they are effectively free-floating, insulated from the rumble of earthquakes, the pounding of ocean waves on distant shores, and even the rumble of local traffic. They operate in the deepest vacuum ever created by humans. Yet, for all this monumental effort to eliminate classical noise, a more fundamental, inescapable barrier remains: the quantum noise born directly from the uncertainty principle. This manifests in two primary ways that shackle the sensitivity of even these perfect machines. First, there is shot noise. Laser light is not a smooth, continuous wave. It is a stream of discrete particles, photons. These photons arrive at the detector in a random, probabilistic pattern governed by quantum mechanics. This randomness creates a constant, hissing static in the measurements. It's like trying to hear a pin drop in a quiet room while also listening to the constant, irregular patter of rain on the roof. You can average it out over time, but for a brief, fleeting signal like a gravitational wave, this quantum rain can easily obscure the delicate sound you're desperate to hear. The obvious solution is to use a more powerful laser, flooding the interferometer with more photons to smooth out the randomness. But this leads directly to the second problem: quantum radiation pressure noise. Remember Heisenberg's trade-off: the more precisely you know a particle's position, the less you know about its momentum. Those countless photons from the more powerful laser, while smoothing out the shot noise, carry their own momentum. As they constantly bombard the mirrors, they deliver trillions of tiny, unpredictable kicks. This radiation pressure causes the heavy mirrors themselves to jitter ever so slightly in their positions. We are caught in a perfect quantum bind. Turning up the laser power reduces one kind of quantum uncertainty only to amplify another. It is an inescapable tug of war dictated by the fundamental laws of physics, a literal manifestation of the uncertainty principle playing out on a macroscopic scale within our largest scientific instruments. This is where a brilliantly clever technique, born from a deep understanding of quantum mechanics, comes to the rescue: quantum squeezing. Instead of fighting the uncertainty principle, quantum squeezing accepts its rules and then cleverly cheats at its own game. The principle tells us we cannot reduce the overall uncertainty of a system, but it doesn't say we can't redistribute it. Imagine uncertainty as a blob of clay. You can't make the blob smaller, but you can squeeze it, shaping it to be long and thin in one direction while it becomes short and fat in another. This is precisely what scientists do with light. Using special nonlinear crystals, they can create a peculiar state of light called squeezed light. This light has been engineered so that the quantum uncertainty in one of its properties, say, the exact timing of its wave peaks known as phase, is drastically reduced. The trade-off is that the uncertainty in another property, like its amplitude or photon number, becomes correspondingly larger. For gravitational wave detectors, this is a fantastic bargain. The phase of the laser light is exquisitely sensitive to the tiny changes in arm length caused by a gravitational wave. By squeezing the light to have less uncertainty in its phase, we effectively reduce the shot noise that was obscuring our signal. The increased uncertainty in amplitude, which translates to stronger radiation pressure noise, is a price we are often willing to pay, especially for detecting the high-frequency gravitational waves from lighter objects where shot noise is the dominant problem. The implementation of this technology is itself a marvel. At LIGO, squeezed light is now generated in a separate, small vacuum chamber and then injected into the main interferometer, effectively filtering the laser light to make it quantumly quieter in the specific property they need to measure. Future observatories like the Planned Laser Interferometer Space Antenna, or LISA, a constellation of 3 spacecraft spanning millions of kilometers, will rely on quantum squeezing from the very beginning to listen for the low-frequency rumble of supermassive black holes merging at the dawn of time. This is not merely an upgrade, it is a fundamental paradigm shift in measurement. We are no longer just building better instruments. We are learning to manipulate the fabric of reality at a quantum level to peer across the universe and further back into its history than ever before thought possible, turning the universe's own fundamental ambiguity into the very tool we use to explore it. This idea of particles influencing each other instantly across vast distances brings us to one of the most baffling and beautiful consequences of the quantum world: entanglement. If the uncertainty principle tells us that particles are fuzzy and undefined until measured, entanglement tells us that the fates of multiple particles can be woven together into a single, inseparable whole, creating connections that seem to defy the very nature of space and time. It's a phenomenon so strange that even Einstein found it deeply unsettling, famously dismissing it as spooky action at a distance. To understand entanglement, let's create a simple pair of hypothetical particles. We'll call them photons for our example. Imagine we have a special process that creates 2 photons and sends them flying off in opposite directions, perhaps to 2 scientists named Alice and Bob, who are stationed in labs light years apart. These 2 photons are entangled, meaning their quantum states are linked. Now, let's say the property they share is polarization, the orientation of their light waves. According to quantum mechanics, until measured, each photon exists in a superposition of all possible polarization states. But here's the magical part: their states are correlated. If Alice measures her photon and finds it polarized vertically, then Bob's photon, instantly and without any known signal passing between them, will be polarized horizontally. The act of Alice's measurement here on Earth seems to immediately collapse the possibilities for Bob's photon, even if it's on the other side of the galaxy. Einstein, Podolsky, and Rosen formulated their famous EPR paradox to argue that this spooky action was proof that quantum mechanics was an incomplete theory. They believed in a concept called local realism, which has 2 core ideas. Locality means that objects can only be influenced by their immediate surroundings, and no signal or effect can travel faster than light. Realism means that particles have definite properties like polarization or spin, whether we measure them or not. To Einstein, it was simply common sense that a particle on Earth couldn't possibly influence a particle near Alpha Centauri without some signal traveling between them, which would take years. He argued that there must be hidden variables, unknown properties predetermined at the moment of entanglement, that dictate what the measurements will be. In this view, the particles are like a pair of gloves. If you separate them and mail one to Alice and one to Bob without looking, and then Alice opens her box to find a left-handed glove, she instantly knows Bob has the right-handed one. There's no spooky action, it was just a fact established when they were packed together. For decades, this was a philosophical debate. Then, in the 1960s, a brilliant physicist named John Bell devised a way to test it. Bell's theorem provided a mathematical inequality that any local hidden variable theory must satisfy. If quantum mechanics were correct and spooky action was real, experiments would violate this inequality. The beauty of Bell's test is that it doesn't require knowing what the hidden variables might be. It simply tests the statistical outcomes of many measurements. The first decisive experiments were conducted in the 1970s and 80s by physicists like Elaine Aspect. They carefully measured entangled particles and tallied the results. Time and again, the results violated Bell's inequality. The universe had chosen. There were no local hidden variables. The correlation between the particles was stronger than any classical, predetermined theory could allow. When Alice measured her photon, Bob's photon really did respond instantaneously, a connection that seemed to transcend the space between them. This doesn't mean information is traveling faster than light in a way we can use for communication. Bob has no control over what state his photon will collapse into. It's completely random from his perspective. He just gets a random sequence of results. It's only when Alice later calls him on a slow, classical telephone, which is limited by the speed of light, and compares their lists that they both see the perfect, spooky correlation. So, while the effect is instantaneous, it can't be used to send a message faster than light. The universe, it seems, preserves causality and the speed of light as the ultimate speed limit for information, but allows for this deeper, weirder connectedness underneath. This profound weirdness isn't just a laboratory curiosity. It's the foundation for a revolutionary technology called quantum cryptography, specifically quantum key distribution. The most well-known protocol is called BB84, named for its inventors and the year it was published. Here's how it uses the principles of entanglement and the no-cloning theorem, which states you can't perfectly copy an unknown quantum state to create potentially unbreakable security. Imagine Alice wants to send a secret message to Bob. First, she needs to send him a random cryptographic key, a string of ones and zeros, that they can use to encrypt and later decrypt the message. If she sends this key over a normal internet connection, a hacker could intercept and copy it without either of them knowing. But if she sends the key using entangled photons, the laws of physics themselves guarantee security. She generates a string of entangled photon pairs, sends one photon from each pair to Bob, and keeps the other. They both then measure their photons in randomly chosen bases. Afterwards, they talk on an ordinary public channel and announce which bases they used for each measurement, but not the results. They only keep the bits where they happen to choose the same basis. Because the photons were entangled, these bits will be perfectly correlated, giving them a shared secret key. Now, here's the magic of security. If a hacker named Eve tries to intercept the photon on its way to Bob, she has to measure it to read the information. But measuring it forces it to choose a state, and she has no idea which basis Alice and Bob will later agree upon. Her measurement will inevitably disturb the quantum system. When Bob measures his photon, the results won't match Alice's perfectly. By comparing a small subset of their key bits over the public channel, Alice and Bob can calculate the error rate. If they see too many discrepancies, they know Eve was listening, and they simply discard the entire key and start over. If the error rate is low, they know their key is secure and can use it to encrypt their message. This isn't just a harder code to break. It's a system where any attempt at eavesdropping is fundamentally detectable, turning the universe's inherent uncertainty into the ultimate tool for privacy. And this brings us to one of the most profound and puzzling connections in all of modern cosmology, where the quantum uncertainty of the microscopic vacuum reaches out to dictate the ultimate fate of the entire cosmos. We've seen how these fleeting quantum fluctuations can create particles and even cause black holes to evaporate. But what if their combined effect wasn't just a curious side effect, but the dominant force in the universe? This is the bold and controversial hypothesis that attempts to solve the greatest mystery in physics today, the nature of dark energy. The story begins with a shocking discovery made at the end of the 20th century. Two teams of astronomers were studying distant supernova, using these stellar explosions as cosmic mile markers to measure how the expansion rate of the universe has changed over time. Everyone expected to find that the expansion was slowing down, gradually decelerated by the relentless pull of gravity from all the matter in the cosmos. But the data revealed the exact opposite. The expansion of the universe is not slowing down, it is speeding up. Some mysterious repulsive force counteracting gravity is pushing galaxies apart at an ever-increasing rate. This discovery was so unexpected and so revolutionary that it earned the Nobel Prize in Physics in 2011. This mysterious force was dubbed dark energy. So what could possibly be causing this accelerated expansion? The leading candidate comes directly from the quantum world and is known as vacuum energy. Remember the quantum foam, that seething sea of virtual particles popping in and out of existence thanks to the energy-time uncertainty principle. Each of these fleeting fluctuations borrows a tiny amount of energy, and according to quantum field theory, this isn't just a theoretical idea, it has a real physical effect. This roiling activity of the vacuum endows empty space itself with a fundamental energy density. Even in a region of perfect nothingness, there is still this underlying hum of quantum activity, a baseline energy that never switches off. And here is where Einstein makes a triumphant, if ironic, return to the story. His theory of general relativity tells us that space-time isn't just a static stage. It's a dynamic entity that can be curved and warped by matter and energy. But his equations also contained a fudge factor he later called his biggest blunder, the cosmological constant, represented by the Greek letter lambda. He originally introduced it to force the equations to describe a static, unchanging universe, which was the prevailing belief at the time. When the universe was later found to be expanding, he discarded the idea. But now, cosmologists realized that Einstein's cosmological constant wasn't a blunder at all, it was a prophecy. If you take the energy of the quantum vacuum and plug it into Einstein's equations as the cosmological constant, it produces exactly the kind of repulsive gravity that would cause the universe's expansion to accelerate. The quantum vacuum's inherent energy could be the dark energy we observe. This seems like a perfect, elegant solution. The uncertainty principle gives us a mechanism for why empty space has energy, and general relativity tells us that energy curves space-time in a way that can drive acceleration. But there's a catastrophic problem, and it's arguably the worst theoretical prediction in the history of science. When physicists attempt to calculate how much energy the quantum vacuum should contain, they do so by summing up all the possible fluctuations across all possible energy levels up to the Planck scale. The number they get is astronomically, unimaginably large. It should be around 120 orders of magnitude stronger than what we actually observe from the acceleration of the universe. That's a 1 followed by 120 zeros. If the theoretical prediction were correct, the repulsive force of this vacuum energy would have been so immense that it would have torn every atom, planet, and galaxy apart instantly after the Big Bang. The universe as we know it would never have formed. The fact that we exist at all means the observed value of dark energy is almost zero in comparison to the theoretical expectation, but it's not quite zero. It's a tiny, faint whisper of a force that just happens to be dominating the cosmos now, 14 billion years after it began. This enormous discrepancy is known as the cosmological constant problem, and it represents a glaring crisis in fundamental physics. It suggests we are missing something deep, something fundamental about how quantum physics and gravity interact. How can the calculated vacuum energy be so enormous, yet the observed effect be so infinitesimally small? Why is it not zero? And why is its value so perfectly tuned to allow galaxies, stars, and life to form before it eventually takes over and begins accelerating the expansion? This isn't just a calculation error, it points to a profound gap in our understanding. Perhaps the quantum vacuum energy is somehow cancelled out or screened by an unknown mechanism. Maybe our understanding of gravity is wrong on the largest scales, requiring a modification of Einstein's theory. Or perhaps the value isn't fixed by law but is a random accident, one value among a near infinite number of possibilities in a vast multiverse. This last idea is known as the anthropic principle. If there are countless universes, a multiverse each with different random values for the fundamental constants, then we naturally find ourselves in one of the rare universes where the value of the cosmological constant is small enough to allow for the formation of galaxies and the evolution of life. We shouldn't be surprised to measure a value that seems improbably perfect. In a universe with any other value, we wouldn't be here to measure it. While this provides a possible explanation, it is deeply unsatisfying to many physicists who seek a fundamental, predictive theory from first principles. The mystery of dark energy powered by the quantum vacuum is now one of the central driving forces of observational cosmology. Projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory are mapping billions of galaxies to measure the history of the universe's expansion with exquisite precision, trying to determine if dark energy is truly a constant cosmological constant, or if its strength has changed over time, a clue that could point toward a more dynamic theory. The quest to understand this link between the quantum void and the cosmic horizon is more than just an academic exercise. It is an attempt to answer the ultimate question of our cosmic destiny. Will the acceleration continue forever, leading to a cold, empty, and isolated fate known as the heat death? Or could the dark energy evolve in a way that leads to a more dramatic end? The answers lie in understanding how the universe's smallest uncertainty shapes its grandest design. Heisenberg's own method for illustrating his radical insight was both elegant and disarmingly straightforward, a thought experiment he called the gamma-ray microscope. Rather than relying on complex mathematics, he grounded his principle in a practical, almost tactile scenario anyone could picture. Imagine you are a subatomic scientist and your goal is to locate a single electron. To see anything, you need light, and to see something as vanishingly small as an electron, you need light with an extremely short wavelength to avoid blurring the image. This is the same reason we use electron microscopes to see tiny objects today. Their effective wavelength is far shorter than that of visible light. For his experiment, Heisenberg proposed using the shortest wavelength light possible, high-energy gamma rays. So you shine your gamma-ray microscope at the electron. A single gamma-ray photon, a tiny packet of intense energy, shoots out and strikes the electron. It bounces off and enters your microscope's lens, allowing you to pinpoint the electron's position with incredible accuracy. You have your answer, but in obtaining that answer, you have utterly lost the very thing you might want to know next. That gamma-ray photon didn't just gently bounce off the electron like a softball off a wall. Because it carries such a high energy, it also carries significant momentum. When it collides with the electron, it delivers a powerful, unpredictable kick, like a cue ball smashing into a single billiard ball on an otherwise empty table. You now know exactly where the electron was at the instant you looked, but you have completely scrambled its momentum. You have no idea where it's going or how fast. Now consider the opposite approach. Suppose you want to gently measure the electron's momentum without giving it a violent shove. To do this, you would use a much gentler probe, a photon with a very long wavelength, like a low-energy radio wave. This photon would deliver only a soft, barely noticeable nudge, leaving the electron's momentum largely undisturbed. You could get a beautiful, clear reading of its speed and direction. But the trade-off is immediate and absolute. A long wavelength photon cannot resolve fine details. It would be like trying to find a single specific grain of sand on a vast, dark beach by scanning it with a giant, diffuse spotlight. The beam illuminates a huge area, giving you a general sense of movement within that glow, but the precise location of that one grain within that area is completely lost. You know how it's moving, but not exactly where it is. The genius of Heisenberg's argument was in showing that this is not a limitation of our technology. It is not that our microscopes are too crude or our photons too clunky. This trade-off is an inescapable consequence of the wave-particle duality of both light and matter. The photon you use to see is both a wave, which defines its resolving power, and a particle, which defines its momentum. The electron you are trying to measure is also both a particle with a position and a wave with a momentum. The act of measurement is an interaction between these two quantum entities, and that interaction forces a choice. You can ask the particle-like question, "Where are you?" and get a sharp answer, but in doing so, you destroy the wave-like information about its motion. Or you can ask the wave-like question, "How are you moving?" and get a clear answer, but in doing so, you sacrifice the particle-like information about its exact location. The universe, it seems, refuses to answer both questions with full precision at the same time. Heisenberg's microscope wasn't just a tool for measurement. It was a philosophical instrument that revealed a fundamental truth, that at the heart of reality lies an irreducible and necessary uncertainty. This inherent quantum fuzziness doesn't just apply to where a particle is or how it's moving. It also governs the very flow of time itself, imposing a fundamental limit on our ability to measure it with perfect precision. This is the energy-time uncertainty principle in action, and it has profound and very practical consequences for the technology we rely on every single day. At its heart, this principle tells us that the more precisely you want to measure the energy of a system, the longer you must observe it. Conversely, if you try to measure energy in an extremely short amount of time, your result will be inherently fuzzy. This isn't a stopwatch error, it's a rule written into the fabric of reality, stating that time and energy are also entangled in a cosmic balancing act. This trade-off becomes spectacularly important when we consider the most precise timekeeping devices ever created, atomic clocks. These aren't clocks with gears and pendulums, they are monumental instruments of quantum measurement. Their operation is a direct application of quantum mechanics. At the core of an atomic clock is a cloud of atoms, often cesium or rubidium. These atoms have electrons that orbit the nucleus in specific quantized energy levels. An electron can jump from a lower energy level to a higher one, but to do so, it must absorb a very specific amount of energy, a precise packet of electromagnetic radiation with an exact frequency. This frequency is the atom's natural resonance, its unique and unchanging quantum fingerprint. The clock works by bathing these atoms in microwaves, tuning the frequency of those microwaves until they perfectly match the frequency needed to flip the spin of the atom's electrons. When the frequency is just right, the maximum number of atoms absorb the energy and change their state. This is the resonance. The clock then uses this perfectly tuned frequency to count the passage of time. 1 second is officially defined as 9,192,631,000. 770 cycles of the radiation corresponding to the transition between two specific energy levels of the cesium atom. The stability of this atomic transition is what makes these clocks so astonishingly accurate, losing less than a second over the entire age of the universe. But here is where the energy-time uncertainty principle introduces a fundamental, inescapable whisper of noise. To measure the energy of that atomic transition, to find that perfect resonant frequency, the clock must observe the atoms for a certain amount of time. The longer the observation time, the sharper the measurement of the energy difference, and thus the more precise the frequency, and by extension, the timekeeping. Think of it like listening for a pure musical note. If you only listen for 1,000th of a second, you might catch a brief sound, but you can't be sure of its exact pitch. If you listen for a full second, you can identify the note with perfect clarity. The atomic clock is listening for the universe's most perfect note, and the length of its listen determines the precision of the tune. However, there's a catch. You can't observe the atoms forever. In practical clocks, the atoms are moving, and eventually they will drift out of the observation zone or interact with the environment. This limits the maximum possible observation time. This means that even our best atomic clocks are ultimately constrained by Heisenberg's rule. The energy of the atomic transition has a fundamental uncertainty, which translates directly into a tiny, unavoidable jitter in the frequency of the clock's tick. We can engineer around this to incredible degrees, using lasers to cool atoms to near absolute zero, slowing them to a crawl to maximize observation time, but we can never completely eliminate the quantum mechanical limit. The universe itself places a final, uncrossable horizon on timekeeping precision. This isn't just an academic concern for physicists. It has a direct and crucial impact on a technology billions of people use daily, the Global Positioning System, or GPS. Your phone or car GPS doesn't magically know where you are. It performs a breathtaking feat of relativity and quantum precision. The system consists of a constellation of satellites, each carrying an incredibly precise atomic clock. These satellites continuously broadcast signals that include their exact location and the exact time the signal was sent based on their onboard clock. Your GPS receiver gets these signals from multiple satellites. Since the signals travel at the speed of light, your receiver can calculate the distance to each satellite by measuring how long the signal took to arrive. If you know your precise distance from 3 satellites, you can triangulate your position on Earth. But there's a catch. This entire system relies on perfectly synchronized time. A timing error of just 1/1,000,000th of a second would lead to a positioning error of over 300 meters. This is why the atomic clocks are so vital. The energy-time uncertainty principle and the resulting limits on clock precision are therefore engineered into the very foundation of GPS. System designers must account for this fundamental jitter. The clocks on the satellites are constantly monitored and corrected from ground stations, and the system uses multiple satellites and complex algorithms to overcome these tiny uncertainties. If our clocks were significantly less precise, if the quantum limit were more severe, the entire system would become unusably inaccurate. The incredible accuracy of modern GPS, which can pinpoint your location to within a few meters, is a testament to our ability to push against the universe's fundamental limits, harnessing the strange rules of quantum mechanics to navigate our classical world. It's a powerful reminder that the quantum fuzziness governing single atoms directly shapes the macro-scale technology that connects our global civilization. Now, let's push this idea of entanglement into a realm that feels like pure science fiction, but is in fact a working laboratory reality: quantum teleportation. The very term conjures images of Star Trek transporters, dematerializing an object in one place and reassembling it perfectly in another. While we're not teleporting people or even coffee mugs, we are achieving something almost as miraculous: the instantaneous transfer of the quantum state of a particle from one location to another. And the most crucial part of this process is that it does not violate the uncertainty principle or the speed of light. Instead, it uses them as essential ingredients in a beautifully orchestrated quantum dance. The goal of quantum teleportation is not to send the physical particle itself, but to perfectly replicate its exact, unknown quantum state onto a different particle some distance away. The original particle is not physically moved. Its state is effectively destroyed in the process of being read and recreated elsewhere. This is vital because of the no-cloning theorem, a fundamental rule of quantum mechanics which states that you cannot create an independent, perfect copy of an unknown quantum state. You can't just scan a particle and send the blueprint to someone else to recreate, because the act of scanning, of measuring it, would collapse its state and you'd only ever get one of its possible properties. Teleportation cleverly sidesteps this by using entanglement to transfer the state without ever actually learning what it is. Here's how this astonishing feat is accomplished step by step. Our story involves 3 particles and 2 people traditionally named Alice and Bob. First, we need our quantum channel, a pair of particles that are maximally entangled. This is our resource. Let's say they are 2 photons. One of these entangled photons is given to Alice, and the other is sent to Bob, who can be any distance away across a lab, across a city, or even, as has been demonstrated via satellite, across continents. Now, Alice has a third particle, let's call it Particle X, whose mysterious quantum state she wants to teleport to Bob. Particle X could be in any state at all, a complex superposition of multiple possibilities, and Alice has no idea what that state is. Her mission is to get that information to Bob so that his entangled photon can become a perfect replica of Particle X. She begins by performing a special kind of measurement on her 2 particles, the one that's entangled with Bob's and Particle X. This is called a Bell state measurement. It doesn't tell her the state of either particle individually. Instead, it measures the joint correlated properties of the 2 particles together. This act of measurement has 2 instantaneous and profound consequences. First, it entangles Particle X with Alice's half of the original entangled pair. Second, and this is the spooky part, because Alice's entangled photon was linked to Bob's, this measurement instantly affects the state of Bob's photon, which is now far away. However, and this is the critical nuance that prevents faster-than-light communication, Bob's photon doesn't immediately become a copy of Particle X. Instead, it is thrown into a seemingly random, scrambled state. Bob now has a particle that has been changed, but in a way that appears completely useless to him. It looks like noise. The magic key that unlocks the teleportation is what happens next. The outcome of Alice's Bell measurement is completely random, and it gives her one of 4 possible classical results. She must now pick up a classical telephone, or send a radio signal or an internet packet, and call Bob to tell him which of the 4 outcomes she got. This classical information, these 2 simple bits of data, travel to Bob at or below the speed of light. Once Bob receives this message, he knows exactly what operation to perform on his now scrambled particle. Depending on the message, he might need to flip its phase, rotate its spin, or do nothing at all. Once he applies this specific correction, his particle instantaneously snaps into the exact, pristine quantum state that Particle X originally had. The teleportation is complete. Let's be perfectly clear about what did and did not happen. The original Particle X was destroyed by Alice's measurement. Its quantum state was erased. No matter was transported, no information traveled faster than light. The only thing that moved faster than light was the spooky, random correlation established by entanglement, but that correlation was useless until Bob received the classical message from Alice. The 2 bits of classical information were the essential ingredient that allowed Bob to decipher the change that had already happened to his particle. This process perfectly respects the cosmic speed limit for information transfer, while showcasing the bizarre, non-local connectedness that entanglement provides. The implications for this are staggering, forming the backbone of the future quantum internet. Imagine a network where quantum information, not just classical data, can be transmitted securely between nodes. Quantum teleportation provides a way to move fragile quantum states between different quantum computers, allowing them to be linked into a more powerful whole. It enables protocols for distributed quantum sensing and secure quantum communication that are fundamentally unhackable, because any attempt to intercept the state during teleportation would introduce errors that the legitimate users could immediately detect. We are moving from a world of simply sending information to a world of sending the very state of existence itself, opening a new chapter in how we connect and compute, all built upon the uncertain, spooky, and profoundly useful foundations of the quantum world. The standard model of particle physics represents our most complete and accurate map of the fundamental building blocks of the universe and the forces that govern their interactions. And at the very heart of this magnificent theoretical framework, acting as its silent, buzzing engine, is the uncertainty principle. It is not merely a feature of the model, it is the very mechanism that makes the forces of nature possible. Every push, every pull, every interaction between particles is mediated by a constant, frenetic exchange driven by the universe's inherent quantum fuzziness. To see this in action, let's consider a force we all know well, the electromagnetic force. How does one electron repel another? In our classical imagination, we might picture a field of influence emanating from each particle like an invisible aura. But the quantum reality is far more dynamic and strange. According to the standard model, this repulsion is actually accomplished through a game of subatomic catch. The energy-time uncertainty principle allows the first electron to spontaneously emit a virtual photon, a transient particle of light that should not, according to classical energy conservation, exist at all. But because its existence is so fleeting, the universe's energy ledger can balance. This virtual photon then carries the electromagnetic force across the gap to the second electron, which absorbs it, and the exchange of this phantom particle communicates the repulsive force between them. This process is not unique to electromagnetism. It is the universal language of force in the quantum world. The strong nuclear force, which glues protons and neutrons together inside atomic nuclei, is carried by virtual particles called gluons. The weak nuclear force, responsible for radioactive decay, is mediated by virtual W and Z bosons. Even the recently discovered Higgs boson gives particles their mass through interactions with a field that is itself subject to quantum fluctuations. In every case, the forces we experience are the macroscopic result of countless microscopic transactions made possible by the uncertainty principle's temporary loan of energy. The universe is not a static collection of particles, it is a seething network of continuous probabilistic exchanges, a dance of virtual particles that weave the fabric of reality itself. Yet for all its stunning success, the standard model is not the final word. It describes 3 of the 4 fundamental forces with breathtaking precision, but it utterly fails to include the 4th, gravity. This is the great unsolved problem of modern physics, and once again, the uncertainty principle is at the center of the storm. The conflict arises when we try to apply quantum rules to gravity. In Einstein's general relativity, gravity is not a force in the traditional sense. It is the curvature of spacetime caused by mass and energy. But when we try to describe this curvature at the quantum scale, where energy is wildly fluctuating thanks to the uncertainty principle, the mathematics breaks down into nonsense, producing infinite results that physicists cannot renormalize or smooth away. Imagine spacetime not as a smooth rubber sheet, but as a foaming, bubbling sea at the smallest scales. The energy-time uncertainty principle means that the energy density at a point is never perfectly defined. It is constantly fluctuating. These fluctuations would cause spacetime itself to warp and curve uncontrollably at incredibly tiny distances and timescales around the Planck length. The very concepts of here and now would lose all meaning in a violent, chaotic quantum foam. Our current theories of quantum mechanics and general relativity are fundamentally incompatible in this realm, telling us that our understanding of the universe is incomplete. This is not a minor technicality, it is a screaming siren that we are missing a deeper theory, a theory of quantum gravity. This profound challenge is the primary motivation for the most ambitious theoretical frameworks in physics, most notably string theory. String theory proposes a radical solution, that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating loops of energy strings. The different vibrations of a string correspond to different particles, much like different vibrations of a violin string produce different musical notes. In this elegant vision, the graviton, the hypothesized quantum particle that would carry the gravitational force, emerges naturally from the theory as a specific vibrational mode of the string. Crucially, string theory inherently respects the uncertainty principle while potentially smoothing out the infinities that plague other attempts to quantize gravity. The extended nature of the string, as opposed to a point particle, appears to soften the violent quantum fluctuations of spacetime that occur at the Planck scale. Furthermore, for the mathematical consistency of string theory to hold, it requires more than the three spatial dimensions we experience. It proposes extra, curled-up dimensions of space, themselves subject to quantum uncertainty in their shape and size. The properties of our entire universe, the masses of particles, the strengths of forces would then be determined by the specific way these extra dimensions are compactified, a configuration that might itself be one possibility among a vast landscape of options. While string theory offers a compelling and mathematically beautiful path to unification, it remains for now a theory beyond direct experimental verification. The energy scales required to probe these tiny strings or the extra dimensions are far beyond the reach of any particle collider we could conceivably build. Yet its very existence and that of other approaches like loop quantum gravity is a direct testament to the power of the uncertainty principle. It is this fundamental limit on our knowledge, this inherent quantum fuzziness, that has driven physics to its most creative and profound heights, forcing us to consider that the true nature of reality may be far stranger and more wonderful than we ever imagined, hidden within the vibrations of impossibly small strings or the intricate geometry of higher dimensional space. This journey into the quantum heart of uncertainty does more than just reshape our physics. It recalibrates our entire approach to knowledge, progress, and our role in the cosmos. Embracing the fact that some things are fundamentally unknowable instills a profound humility in our scientific and technological pursuits. For centuries, the dream of a clockwork universe promised ultimate prediction and control, a world where enough data would yield perfect answers. The uncertainty principle shatters that dream, replacing it with a more nuanced and mature relationship with reality, one built not on conquering nature, but on collaborating with its inherent complexity. This shift from a mindset of certainty to one of guided exploration has ripple effects that extend far beyond the laboratory, deeply influencing the ethical dilemmas we face at the frontiers of technology. Consider the explosive development of artificial intelligence. We are building systems of staggering complexity, neural networks with billions of connections whose decision-making processes are often inscrutable, even to their creators, a modern phenomenon often called the black box problem. This isn't just a technical challenge, it's an ethical quagmire. When an AI system recommends a medical diagnosis, approves a loan, or influences a judicial decision, we are entrusting immense power to a system whose internal logic we cannot fully trace. The classical desire would be to tear the box open, to demand perfect transparency and deterministic certainty in its outputs. but the lessons of quantum mechanics suggest a different path. Perhaps like an electron, a complex AI system does not possess a single, definite reason for its output until we interrogate it, and the act of interrogation itself changes the result. This doesn't mean we surrender to algorithmic mysticism. Instead, it forces a more sophisticated ethical framework. We must shift our focus from demanding impossible levels of internal transparency to rigorously auditing external outcomes, building systems that are robustly aligned with human values even if their internal workings remain probabilistic and emergent. We must design for uncertainty, creating AIs that can express confidence intervals in their decisions, that can flag when they are operating outside their trained parameters, and that are built with fail-safes that acknowledge the potential for unpredictable behavior. Accepting uncertainty here isn't a concession. It's the only prudent way to manage the risks of technologies whose complexity begins to mirror that of the natural world itself. This same principle applies with even greater urgency to biotechnology and genetic engineering. Tools like CRISPR allow us to edit the code of life with increasing precision, offering cures for hereditary diseases and the potential to reshape ecosystems. Yet, every intervention in a biological system is an exercise in navigating uncertainty. A genome is not a linear, deterministic blueprint. It's a complex, interactive network where editing a single gene can have cascading and unforeseen effects, a phenomenon known as pleiotropy. We can precisely snip a DNA sequence, but we cannot perfectly predict how the living, evolving system will respond over time. This inherent biological uncertainty makes a strong ethical case for the precautionary principle. It argues for careful, incremental testing and a deep respect for the interconnectedness of living systems. The goal cannot be to achieve total control over biology, but to guide it with a humble acknowledgement of the things we cannot know, the long-term evolutionary consequences, the potential for unintended effects on ecosystems, or the societal impacts of fundamentally altering what it means to be human. The most ethical stance in biotechnology may be one that actively incorporates uncertainty into its decision-making models, valuing resilience and adaptability over rigid, predictable outcomes. Ultimately, this embrace of uncertainty fosters a healthier relationship between science and society. It moves us away from the outdated model of the scientist as a priestly figure delivering immutable truths, and towards a model of science as a continuous, collaborative, and error-correcting process. It makes science more human, more fallible, and ultimately more trustworthy because it openly acknowledges its limits. In a world grappling with challenges from climate change to pandemics, where complex systems create inherently unpredictable outcomes, this intellectual humility is our greatest asset. It encourages open dialogue, continuous learning, and adaptive governance, reminding us that the goal is not to eliminate all risk or know all answers, but to build a society that is resilient, thoughtful, and wise enough to navigate the unknown together. But the true power of quantum sensing is moving beyond simply detecting these tiny signals to actively canceling out the noise that has always plagued conventional measurements. This is where a technique called quantum squeezing performs what seems like magic, manipulating the uncertainty principle itself to our advantage. Remember how Heisenberg's trade-off means you can't simultaneously know two linked properties, like a photon's amplitude and phase, with perfect precision. Quantum squeezing accepts that rule but cleverly redistributes the fuzziness. Scientists can use nonlinear crystals to create squeezed light, a special quantum state where the uncertainty in one property is drastically reduced. The inevitable trade-off is that the uncertainty in the other property increases, but if that second property is less important for your specific measurement, you gain a massive advantage. In gravitational wave observatories like LIGO, injecting this squeezed light into the interferometer reduces the quantum shot noise that obscures the signal, allowing them to listen for fainter cosmic events. This isn't just a better filter, it's a fundamental re-engineering of light at the quantum level to see what was previously invisible. The next generation of these sensors will use this principle to listen for the primordial rumble of the Big Bang itself, pushing the boundaries of what we can observe. This technological revolution is now moving out of massive laboratories and into compact, practical devices poised to transform entire industries. One of the most promising near-term applications is in quantum magnetometry. These are sensors that can detect magnetic fields with a sensitivity that is almost incomprehensible. A modern quantum magnetometer can detect a magnetic field 1 billion times weaker than a refrigerator magnet, and 1 million times weaker than the subtle magnetic field generated by the human heart. They often use nitrogen vacancy centers in diamond atomic scale defects where the spin of an electron can be manipulated and read out with laser light, making it exquisitely sensitive to minuscule magnetic fluctuations. The applications read like science fiction. In medicine, they could be used to create magnetoencephalography, or MEG, systems that map the brain's neural activity without the need for cumbersome, supercooled helmets, potentially revolutionizing the diagnosis of neurological disorders like epilepsy and Alzheimer's. In geology, they could be deployed on drones to pinpoint underground mineral deposits or oil reserves with unprecedented accuracy from the air. And in security, they could form the backbone of ultra-sensitive scanners capable of detecting even non-metallic threats with a passive, non-invasive sweep. Perhaps the most dramatic demonstration of this new power is emerging in the field of quantum radar and LiDAR. Traditional radar systems work by sending out a radio wave pulse and listening for its echo. But discerning a small, stealthy object against a background of clutter is incredibly difficult. Quantum radar proposes a solution rooted in the spooky connections of quantum entanglement. The idea is to generate pairs of entangled microwave photons. One photon, dubbed the signal photon, is beamed out toward the target. Its entangled twin, the idler photon, is kept securely at the receiver. When the signal photon bounces off the target and returns, it is inevitably degraded and mixed with background noise. However, because it was once entangled with the idler photon, their quantum states remain correlated. By performing a quantum measurement comparing the returning photon with the stored idler photon, the system can distinguish the true echo from the random noise with a success rate impossible for any classical radar. This could render current stealth technology designed to absorb or deflect classical radar waves completely obsolete. While still in early development, the potential for such a system extends to medical imaging, where it could lead to scanners that see inside the human body with cellular resolution using non-ionizing radiation, eliminating the risks associated with X-rays and CT scans. The culmination of all these advances points toward a future where quantum sensors are not specialized tools for physicists, but are integrated into the very fabric of our daily technology. We are moving toward a world where your smartphone's navigation doesn't rely on easily blocked satellite signals, but on an onboard quantum accelerometer that tracks its own position with perfect accuracy, even deep underground or underwater. Where autonomous cars don't just see the road with cameras and LiDAR, but can perceive the magnetic fingerprint of every vehicle and object around them, navigating safely through zero visibility fog. Where archaeologists can map entire buried cities from the air by detecting the faint magnetic disturbances of ancient foundations, and where doctors can diagnose a disease like cancer at its earliest stage by detecting the unique magnetic signature of a few aberrant cells circulating in the bloodstream. This is the ultimate promise of harnessing quantum uncertainty, not to build a better version of what we already have, but to forge entirely new senses for humanity, allowing us to perceive the hidden layers of reality that have been whispering just beyond the limits of our perception all along. Perhaps the most persistent and understandable misconception about the uncertainty principle is the idea that it's merely a statement about our current technological limitations. that if we just had better, gentler microscopes, we could finally pin down an electron's position and momentum simultaneously. This view treats the principle as a symbol of human ignorance, a temporary barrier on the road to complete knowledge. But as we've explored, Heisenberg's insight was far more radical. It's not that we are clumsy observers shaking the system too much. It's that the system itself does not possess those two definite properties at the same time. The uncertainty is not in our measurement. It is in the very nature of the particle's existence. This crucial distinction elevates the principle from a practical challenge to a profound statement about the architecture of reality itself, telling us that the universe at its most fundamental level is not a collection of tiny billiard balls with fixed trajectories, but a tapestry of probabilities and potentialities. This confusion often leads to a second, more philosophical misunderstanding, that the uncertainty principle is a form of postmodern doubt, suggesting that all knowledge is relative or that reality is entirely subjective. This isn't the case either. Quantum mechanics is arguably the most precise, predictive, and rigorously tested theory in the entire history of science. The mathematics of the uncertainty principle gives us exact, quantifiable limits on what we can know. It doesn't say anything goes. It gives us a very specific recipe for the trade-off between observables. This isn't a descent into philosophical chaos. It's a step into a more nuanced, non-intuitive, but still rigorously defined understanding of the world. The rules are different, but they are still strict mathematical rules. The universe isn't ambiguous because it's lawless. It's ambiguous because its laws operate on a logic that defies our everyday experience. These misconceptions aren't just harmless academic mix-ups. They have a real cost, especially when it comes to inspiring the next generation of scientists and engineers. When students are taught that the principle is just about our clumsy tools, it reduces one of physics' most breathtaking ideas to a mere engineering problem, stripping it of its wonder. Conversely, presenting it as a form of mystical, anything-goes subjectivity can alienate those who are drawn to the precision and logic of science. Accurate communication is therefore not just about getting the facts right, it's about framing the wonder correctly. It's about showing that the universe's limits are not walls that stop us, but puzzles that invite us to think more creatively. The most inspiring message we can share is that the universe has rules, but those rules are far more strange and beautiful than we ever imagined. This is where the role of the educator and science communicator becomes so vital. The goal isn't to simplify the weirdness away, but to equip students and the public with the right metaphors and models to appreciate it. We can use the analogy of the mosquito in the dark room with the flashlight not as a perfect representation, but as a bridge to understanding the inherent trade-off. We can explain that asking a particle for its exact location is like demanding a single, frozen answer from something that naturally exists as a spread-out wave of possibility. The act of measurement forces it to choose, and in making that choice, other information is irrevocably lost. This framing preserves the profundity of the concept while making it accessible, turning a potential source of confusion into a source of awe. Ultimately, clearing up these misconceptions is about more than just pedagogical accuracy. It's about fostering a scientific temperament that is comfortable with complexity and comfortable with not having all the answers. It teaches a powerful lesson in intellectual humility, that our intuition, shaped by a macroscopic world, is not always a reliable guide to the underlying nature of reality. And simultaneously, it cultivates a sense of optimism, showing that human ingenuity can not only discover these profound limits, but can also learn to work within them, and even harness them, to create technologies from lasers to MRI machines that transform our world. By communicating the true nature of the uncertainty principle, we don't just teach physics, we invite everyone to participate in the grand, ongoing human adventure of mapping the astonishingly strange and wonderful universe we call home. And so we find ourselves at the end of this journey, not with a final answer, but with a far more profound and lasting gift, a new way of seeing. The uncertainty principle does not build a wall at the edge of knowledge. It opens a gateway to a deeper, more dynamic relationship with reality itself. It teaches us that the universe is not a static collection of facts waiting to be catalogued, but a living, breathing dialogue of potentialities. And we are not just passive observers, but active participants in that conversation. Our every measurement, our every question is part of that dance, shaping the answers we receive and reminding us that the cosmos is far more interactive and wondrous than a mere clockwork machine. This fundamental limit is not a failure, but a feature of existence, the very reason our universe is capable of such breathtaking complexity, creativity, and life. Without this intrinsic ambiguity, there would be no quantum fluctuations to seed galaxies, no delicate balance allowing atoms to form, and no driving force behind the relentless engine of evolution. The same quantum fuzziness that prevents us from knowing everything is the very source of everything we know. It is the reason a laser can produce a beam of perfect coherence, the reason an MRI can peer into the soft tissues of our bodies, and the reason our most powerful computers can hum with potential. Our technological mastery is not achieved by overcoming uncertainty, but by learning to speak its language and harness its rules. Ultimately, the greatest lesson Heisenberg's principle imparts is one of humility and boundless curiosity. It calls on us to let go of a childhood desire for absolute certainty and to embrace the mature, thrilling adventure of exploration itself. The questions we cannot fully answer are not in points, they are the compass points guiding us toward the next great discovery. They are the reason scientists are now probing the quantum nature of life, building computers that calculate with possibility, and listening for the gravitational echoes of black holes. The frontier of the unknown is not receding. It is expanding in every direction, inviting us to look closer, think deeper, and imagine more wildly than ever before. So the next time you feel a question forming or a sense of wonder at the world's complexity, remember that you are touching the edge of this great cosmic mystery. Your curiosity is the most human response to a universe that is fundamentally built on it. This is not the end of understanding, but a beautiful beginning. The story of quantum mechanics is still being written, and its next chapters promise to be the most astonishing yet. Stay curious, stay amazed, and join us next time as we continue to explore the wonders waiting just beyond the known.